Hello and welcome to this homework help video where we're going to talk about three problems that involve thermodynamics. In the context of my other homework help videos, this is actually the second one that covers thermodynamics, but this one has a focus on phase changes, whereas the last one just had a focus on calorimetry, specifically, this is funny, specific heat, okay, which is changes in temperature rather than changes in phase. Okay, so our first problem here is a plug and chug problem, and we have a single key equation, which I'll go ahead and box off. And what this equation tells us is that Q, which represents heat, is equal to mass multiplied by this special value called latent heat. And what latent heat is something similar to specific heat because it's a material specific constant. So glass has a certain latent heat when it changes from a solid to a liquid. Water has a certain latent heat when it changes from a solid to a liquid, from ice to water. And it has a different latent heat when it changes from a liquid to a gas. So in the case of water, from liquid water to water vapor. So there's always two latent heats for every substance. There's what's called the latent heat of condensation or, a condensation. And then the other is the latent heat of vaporization. So vaporization, when you go from a liquid to a gas, condensation, when you go from a solid to a liquid. So two different values, you'll be given the value or asked to find it for a mystery material. In this case, we're given the value because let's take a look at our problem. And we should think we will be given the value because it's a plug and chug, which means we're going to be given the mass and the latent heat, and we just need to find Q, okay? Q is going to have units of joules. It's going to be our final answer. Okay, so with that single key equation, we are asked to calculate the quantity of heat needed to turn 160 grams of 100-degree Celsius water to steam at that same temperature. By the way, phase changes never involve a change in temperature. You change phase once the phase change is complete for that entire sample, that entire substance, in this case, all 160 grams, then you have, then a temperature increase of the water vapor, the new phase, okay? And so let's go ahead and actually change this value, and we're gonna make it 220 grams, but otherwise we keep everything the same, because this is actually a real constant. This is the value that applies to that vaporization latent heat I mentioned. This one is in units of calories per gram. That's fine. There's a different value, which is about 2.3 million, and that's joules per kilogram. What they all have in common is energy, right? So energy per mass. So E, right, for energy per M for mass. So that's what the quantities are, what the ratio is for this material specific value, latent heat. All right. And sometimes it's just shortened as heat, right? It just says the heat of vaporization. It doesn't even actually say the latent heat, but it could if it was being more thorough. Okay? All right, so you think of that as basically a shorthand. All right, let's write it out, and then we'll plug it into the calculator. Okay, so we're going to have our Q. That's what we're solving for. And our first value is going to be the grams. And because our latent heat is given in calories per gram, we want to leave it in grams. Okay, so this is the case where you leave it in grams, so your final answer is in calories. You don't want your final answer to be in joules unless you're given the latent heat or specific heat in joules. Okay, but this one's calories. Okay, so 540 calories per gram. You can see that our grams are going to cancel out, so our final answer is just going to be calories, and it's just going to be the product of 220 times 540. Okay, so two significant figures, it's going to be 120,000. Okay, so we write it right here. We'd have 1.20 times 10 to the fifth, which is the same as 120,000, and I almost wrote joules, calories. Okay, now a calorie is a lot. It was not a lot bigger, but it is bigger than a joule. So a calorie is 4.16 joules, and then a kilocalorie is 4,160 joules. What's a kilocalorie? It's just 1,000 calories. All right, but this is basically just over 4 joules per calorie. That's the unit we're working with here. All right, let's go on to the next problem. You can see that first one was hopefully pretty straightforward. So in problem 2, we have another phase change. So let's check out what's going on. All right, so we have actually a amount of mass we're going to try to solve for here. So we're not going to be solving for the energy this time. Okay, so we're asked for what mass, or find the mass, of 0 degrees Celsius water, okay? So that's water that is at the temperature threshold to melt, right? Because it melts at 0, it boils at 100, okay? So which will completely melt by 90 grams. And when it says by, this is like caused by. So we're asking, what mass of ice will be melted by this much steam, and specifically this much steam at 100 degrees. Why does it matter that it's 100 degrees? This is basically just the problem, making sure that it gives you the value that requires you to only do a latent heat calculation. In other words, you don't have to worry about the steam cooling, in which case you would need to combine a latent heat with a specific heat equation. So you'd have the sum of those two heat flows and the sum of the calories, the sum of the joules of your answer. But in this case, because this value is not bigger than 100, because it is exactly 100, there's just a phase change. All right, the steam will turn into water. The ice is going to melt. Eventually, they're all going to turn into some water at an equilibrium temperature. So you have an equilibrium reached, but we don't care about the final equilibrium here. We just need the ice to melt. We just need it to become water. And you know what? Water at 0. That's the key idea. All right. So what values? Let's see. So we're going to need our, not the heat of vaporization, but our value for melting. Okay. So let's see. Did I give you this one? Specific heat capacity of ice. All right. So we'll need this for the problem 3, but we won't need it here. And I think they wanted you to look this one up for the amount. I'm just double checking that it's not stated because sometimes the smaller fonts I miss. Okay, so what we need is a comparable value, and we can go ahead and get the calorie value because that's going to work out best. Okay, so let's go ahead and so we want a latent heat of condensation in calories. I'm just gonna look that up real fast. Looking online. In this case, at least I'll know what to look for. So 600 calories per gram of liquid water. The process requires 600 calories. This is going to be, that's for vaporization, right? So that's the one we had before. So we have 540 there. All right, so we want, okay. All right, evaporation is called condensation. Okay, yeah, so I'm using, yeah, okay. So what I want, I'm sorry about that. I was using the wrong term. The latent heat what we want is called, let's see, so it's the latent heat. I'll go ahead and bring this up so you can see it too. So we want this is actually a figure that you'll see at the bottom of this homework help, but we want the latent heats of water, and I need to get that correct term. I'm just drawing a blank on it. And so we want a fusion. Excuse me there. And maybe actually if I look down at my figure, we would have had it, but let's go double check out here. So we have, latent heat of fusion. So I could have looked, right? So I included the figure mostly because it tells a good story in its scale. More on that in just a second. But sure enough, we have our value right here. Okay. Now, by the way, this is not in the correct units because we want to work in calories per gram rather than, in this case, kilojoules per kilogram. So essentially, the way you'd read this is 330,000 joules per kilogram is the amount of energy it takes to, melt ice into liquid water. So that's the latent heat of fusion. So let's get the latent heat of fusion, but in calories. So latent heat, okay, so we'll go back over here, and it's going to be 79.7 calories per gram. Okay, so that's the only constant that we didn't have in the units we wanted it in. So you would have been expected to look that up in the book, but here is a good help on it. So 79.7 calories per gram. I'm just going to double check I wrote that down correctly because I was talking while I wrote it. Okay, looks good. And so that's going to be our LF for our latent heat of fusion. Sorry, I was calling it condensation. Condensation is just another term for the latent heat of vaporization. They're totally interchangeable, right? Because one is just going one way, the other is going the other way. Condensation, vaporization, same amount of energy, right? One is absorbing energy, one is releasing energy. Same case with fusion, right? Whether you're going from ice to water or water to ice, it's always going to be latent heat of fusion. So you can see there's just two cases. There's L with the subscript V, which is always 540 calories per gram, so a lot bigger. And then the latent heat of fusion, L sub V, so subscript of F, Okay, so V for vaporization, F for fusion, and you can see it's just short of 80. So I mean, we're talking five times smaller in terms of the actual amount of energy it takes for a given quantity to be melted versus vaporized. So it takes a lot less energy to melt things than it does to boil them. Okay, which makes sense, but it's striking how much less energy, right? A factor of 5. Okay, so with that, we are good to go to find our mass. The equation we're going to use is actually the same key equation, right? So the same key equation from 1 is also going to be our key equation for 2. The difference is that we have to do some algebra. Okay, so the algebra necessary is going to be let's write it out. So we have Q equals M times LF. Okay, so it's the same equation. The only thing I've done is I've swapped out LV for LF because we're talking about fusion instead of vaporization. That's how I was saying. Now we want to solve for M, so all we need to do is just divide both sides by our latent heat of fusion term, the one I looked up. I couldn't remember it, okay, which means it cancels out on the right-hand side, and we're just going to be left with M by itself. And as we write it to solve for M, we see it's just Q divided by that latent heat of fusion. Okay, units totally make sense too, because let's plug them in over here, plug it in red. If we put in our value, okay, so we have our Q value, okay, we'll have to find it, so we'll come back to that. So I'll show you. So that's going to be using the same equation one more time. So we have the same key equation, but we use it twice and combine it. All right, not something we've done before, actually. Okay, basically set it equal to itself, right? Because we're given two pieces of information. But what I do want to point out is that in the denominator, we're going to have that value, the 79.7 calories per gram. And up top, we're just going to have calories, okay? And where do we get the calories from? Well, it's going to be the Q that's released from 90 grams of steam condensing. Because I said it has to absorb energy to go from water to steam, but when steam condenses, it releases that energy. But releases the energy with that same latent heat term, the bigger one, the L sub V, LV terms. So it's just going to be M times LV. I mean, just plug in the numbers here. So it's going to be the mass of the steam, okay, because we're given two different masses. That's why I have to use the equation twice, the single key equation here. So 90 grams times 540 calories per gram, right? So you can see our grams are going to cancel. We're just going to get calories. And that's going to become the value that we put right in here. All right, so let's calculate it over here. 90 multiplied by 540. Looks good. All right, so right here, Q, okay, and this is Q released, is going to be 4.9, right? If I'm going to write it as a rounded value to two significant figures, times 10 to the fourth calories. Good, okay, not joules, because we're working in calories here. All right, so that's the value that's going to go right up here, 4.9 times 10 to the fourth calories, because since that's the energy released from the condensing steam, that is the energy that will be absorbed by the ice, and that's going to make a certain amount of mass melt, right? A certain amount of mass of ice, and that's what we're finding. All right, so this right here will be our mass of ice, our final answer, mass of ice. All right, and I wrote a rounded value, but I won't use a rounded value, so I'm going to go ahead and actually just call this Q. All right, and then we're just going to take that Q variable that I saved by defining it and divide it by 79.7. And it looks like it's going to be 609, all right? But actually, even with the 0.7 here, it would round up to 610, right? And then the two significant figures would round there anyway. So we're going to have 610 grams. That is our answer. All right, 610 grams of ice. So a lot more ice melts, right, compared to how much steam condensed, because there's way more energy in the process of condensing steam than there is in melting ice. All right, as indicated by the much larger constant, right, for latent heat of vaporization, 540, compared to the latent heat of fusion, only 80, right, or 79.7. All right, last one, we're going to basically use this again, but we're also going to kind of have a follow-up question here in part B where we have to look at a ratio, which can be conceptually a little confusing. And you already saw the figure, but I couldn't help but include this. This is a great figure that shows that you can have, right here, you can have like ice at absolute zero, right? So 0 degrees, okay, here's 0 degrees Celsius, all right, right here. But then right here is not 0 Celsius, but absolute zero, which is negative 273 Celsius, right? Why such a strange number? Well, because that's 0 Kelvin. And the offset between Kelvin and Celsius is 273. That's absolute zero. Nothing is actually at absolute zero as far as we know. It's just a theoretical absolute value where all gases would become, eventually condense and all molecular motion would stop. So that's the idea, is we have that happening, right? But you can tell that there is a lot less energy to get down to that lower value, right? So there's much less energy to get to that negative 273 because it doesn't take that much to get there compared to the phase changes, right? Where there's no change in temperature, but you have a lot of heat to add, right? You have to add a lot of heat per kilogram or a lot of heat per gram, right? And then the same thing for vaporization, but look how much more it is, right? This horizontal length is indicative that you have to add a lot more energy because the horizontal axis is a steady rate of energy being added. So the fact that it is a long horizontal line with no temperature change to overcome vaporization shows how much more energy it takes to overcome that phase change as compared to the melting phase change, and also compared to these little linear parts, these diagonal parts, because this is the part where you actually have specific heat, you have temperature change and no phase change. But you can see comparatively, yeah, that might be maybe more energy than the melting, but it is, even though it's marginally more than a certain amount of mass was, had to absorb in order to melt, this horizontal distance here is still a lot smaller than this very large horizontal distance for vaporization. So the biggest share of energy is going to happen at that final step. So you add a bunch of energy, sure, to go all the way from absolute zero, so the coldest possible ice you could have, up to water that's about to boil, right? It's a significant amount of energy. Be going all the way, from here to here. But then look how much more just to get that last step, to then finally boil that liquid water at 100 degrees Celsius and turn into water vapor. Okay, right? So it's kind of interesting. There's so much in that last step. Watch pot never boils because that last step takes way more energy than everything that led up to it. And you're never going to start with ice that's that cold, right? You're going to start with ice that's probably just a couple degrees below 0 degrees Celsius. Okay, maybe a few tens, but certainly not 273 of them. So that absolute value is not something you usually have to memorize, right? But you can always reference it. It's often given in the problem as it is here. So we're told that absolute zero is none other than negative 273 degrees Celsius, okay? Which is 0 Kelvin, as I said. All right. And we're asked to find the quantity of heat needed to change 1 gram, right? So nice even amount, ice at that unbelievably cold temperature, all the way up to 1 gram of boiling water, okay? So what this looks like, our key equation is kind of similar. Okay, it's going to be Q, okay, but it's going to be the sum of different individual Qs, right? So we call this Q total. So think of this as the total heat, and it makes sense to call it total because there's definitely different steps here, right? We have to warm the ice, right, from negative 273 up to 0. Then we have to melt the ice. Then we have to warm what's now water, right, which started as ice, and then we have to boil it, right? So there's 3 steps, okay, or 4, I guess, right? So there's Q, warm the ice. Yeah, I think it's 4, but I'll write them out. Q, melt the ice. Q, warm the water. And, right, because now what was ice is now water. Plus finally, Q, boil the water, right? Or vaporize it. They're very interchangeable terms. If you read in the book, there's a strict definition, difference between them. But here, vaporize, boil, in everyday language, totally fine, totally interchangeable. Vaporize water, okay? And then it'll become water vapor. And we could actually continue to heat the water vapor, right? You can see here, you can heat the steam, but we're not interested in that. We're going to stop once it becomes steam or water vapor at 100 degrees Celsius. All right, so looks complicated, but every one of these is just that same key equation. We're just going to use it again. We're just going to use it 4 times and sum the values together. The one caveat, though, is we're also going to use something from chapter 6. We've got to use the specific heat value, too. So we're going to use the equation from chapter 6, where we had mass times specific heat times temperature change. And then we're going to use our new one here, where we just have mass times latent heat. Okay, so you'll see it all together. Hopefully it all makes sense. Okay, so Q total. Right here, I'm gonna basically write in all the variables now. So here we have, for Q warm ice would just be M, right? And there's just our only M value is this one. So we're just calling this M, okay? It's the same M throughout. And then it's gonna be L, oh, not quite. It's gonna be C ice, right? Which we are given somewhere, okay? Because we're told, there it is. The specific heat capacity of ice, I mentioned earlier when I was looking for the other constant, is 0.5 calories per gram. This is noteworthy because the specific heat of water, the only other one we need for this problem, is 1. It's 1 calorie per gram. That's actually where the calorie comes from, right? So it's exactly calibrated to be exactly 1 calorie per gram. Turns out ice is about half that. So it takes half as much energy to change the temperature of ice by 1 degree Celsius as it does to change the temperature of liquid water by 1 degree Celsius. Now, we're not interested in actually, heating up that steam, but if we wanted to continue to add energy and get the steam to be hotter and hotter up to, say, 200 degrees Celsius or something, because it could just keep going, eventually to become a plasma, you'd ionize it, and that's kind of its own phase change, but not beyond the context of this chapter. But anyway, so it would actually be about the same amount of energy. It would be very comparable to the ice. We could round it, practically speaking, to just call it 0.5 as well. So it's kind of interesting. You got 0.5 on both sides, right, to heat ice and heat water vapor, and then right in the middle, you got 1 calorie per gram for actually changing the temperature of liquid water. All right, so M ice, right, that's just M times C ice, that 0.5 calories per gram, times delta T, change in temperature, and I'm going to call this delta T ice because we have another delta T. This is just the delta T for going from the negative 273 to the 0. So this is warming up that really cold ice. Okay, it's the bigger of our two delta T's, but not necessarily the bigger of our two Q's, and you'll see why. Well, will it be, I guess, because it actually will be even a little bit bigger than the next one. All right, and then we're going to have Q of melt ice, which is going to be M, same M, so it's 1 calorie, and then times LF, because it's the fusion phase change, right, changing from ice to water, and we're adding energy at every step here. And then we'll have that same M again, and then we're going to have C water, okay, and I'm going to write this out, but that's 1 calorie per gram, and then times delta T, water, okay, that's going to be 100. Okay, that's a number, and it represents 100 degrees Celsius. So a change from 0 degrees Celsius up to 100, so a delta of 100. And then finally, our last phase change, same M again, and LV. All right, sorry about that. And LV is that bigger latent heat, the one that was 540 instead of 80. Okay, this one. All right, let's plug in all our values. I'm going to zoom out just a tad. All right, so I'm going to go over here, get a thicker pen for this one, and let's plug them all in before we put them, or write it out what we're going to write before we put it in the calculator. So the 1 is just going to factor right out, so I just have 1 gram here, because it's in every term, all right? So technically that's algebra, right? Because look, the M is in every single term, so I could just factor it out, like so, which means it would be in the front of the parentheses, and it wouldn't be on any of these other terms. Because I divided every term by M, right? So now it's outside of it. We could distribute it back in, but this is a lot easier, right? So we have that M out in front, and the first term, 0.5 calories per gram for the specific heat of ice. All right. Then delta T, I almost wrote 100, but this is the 273. It's positive because we're adding energy, okay? 273 degrees Celsius, all right? And you know what? This should be calories per gram degree Celsius because the units of specific heat are calories per mass per temperature, whereas the units of latent heat is just calories per gram because it's not dependent on temperature change because there's no temperature change when there's a phase change, okay? So I got to put the correct units there on our value, and you can see them up here too, right? If you look for, right, you can see that when it talks about specific heat, it's different, right? The denominator has because this is all in the denominator. They never put parentheses on it, but you could be a little bit more clear, right, like that, right? And notice those are different units than when you're given a latent heat like this one over here, right? Notice the only thing in the denominator is G, right? So no temperature there. All right, so then speaking of which, let's get a latent heat term down. This is going to be that smaller one, the 79.7, so close to 80. Like I was calling it 80 calories per gram, see, right, the units. And then the water one, which is just 1 calorie per gram degree Celsius times 100. Again, it has to be positive, the Celsius there, Celsius, because again, we're adding energy. So all 4 of the terms need to be positive. When I say 4 terms, right, 1, 2, 3, and then the 4th one I'm just about to write, and it's just that one, the LV. Okay, so, and I don't have space for it, so why don't I just write it on the next line and I'll close parentheses, and I think it'll be clear enough, all right? Maybe I can take this whole thing, make it a tiny bit smaller. All right, so let's finish it off over here. Okay. Okay, so last term plus, yeah, this is the big one, 540 calories per gram. Close parentheses. All right. This is going to be the total amount of energy in calories. All right. You can get the total amount of energy in joules, right? But it is mass dependent, you know. So this is a nice, you know, kind of nice value because it's all per gram and we're working at exactly 1 gram, right? So this is kind of the cleanest case. All right. It'd be like if you were doing the joules per kilogram and you're working at 1 kilogram. So we have a 1 in front, obviously not going to affect our answer, but I'm going to put it in there to be hopefully to be clear. And then our 0.5, how do you get on the right like this? 0.5, just to be clear. And then times 273 plus 79.7 plus, and then here 1. Okay, this is not the 1 gram, right? Rather, this is the specific heat. It's just another value. It's exactly 1. And then times 100, right? Speaking of round values here. And then, oh, not multiplied, plus 540. So there you have it. All right, 856. 856. All right, which is probably too many significant figures, but it will. I think a program would take it. Otherwise, you could round this to 860. All right, so either way, and calories. Nice. All right, so that's our answer. In part B, well, that's our answer for A. Part B, we're asked, how does this number of calories compare with the energy needed to simply do that last step, to do the, you know, the 1 gram of, you know, of boiling up to, you know, so the 1 gram of water at 100 degrees to 1 gram of water vapor at 100 degrees. So just the phase change of boiling, okay? Just the phase change of vaporization, okay? Because, yeah, and in this one, yeah, because we had it, oh, I see. I made a mistake. Because look, it didn't say we're boiling it. We're just bringing it to boiling water. So as written, there is not this term at all. See, because I misread it. The problem's asking to bring the ice up to boiling water. All right? So let's go ahead and put that there. So there's no vaporization term because we just got it up to be 100 degrees water. We never actually boiled it. So you can see that that's going to get rid of a big part of it, right? Just check it out, right? That's, you know, actually, it'll be interesting to see. So I'll leave that 856 calculation because that is the energy it would take to go all the way, you know, from super cold ice up to water vapor, so it's boiled. If we had it again, so like we could duplicate it here. Okay, done. And then I'm just going to delete that 540 part. So now it's all the heating, but without the boiling. And that's going to be 316. We'll round to 320 calories. Big difference, right? It's precisely 540 calories less. So then, right, then if we look at the ratio here, we know the water to steam, that step, right, is just 540. You can confirm it here because 856 minus 316 is 540, but of course it is because it's 540 calories per gram. So then we know that this ratio, the heat it takes to boil 1 gram of water into steam will be, right, so I'll write it out. So Q water to steam. That's kind of what they mean when they had with the dash, right? Because it's the water to steam phase change. And then this is going to be the Q that we found above, that's written down in the denominator, the ice, in particular, ice at absolute zero, all the way to water at 100. All right? So, and it's clear up here. So how does this number of calories, right? It's referring to the previous one. So then, okay, because otherwise this notation is a little unclear, right? You know, like what is ice slash water, right? Well, that's just the value you got in part A. Okay, so then we have 540 up top calories per gram, and then as I was saying down below, just be the 316, which I'll write in the rounded value 320. Right, so that's our ratio. That'd be our answer, 540 over 320, or specifically, let's call this. Give it a name. I'm going to call it Q or define it, right? And then we'll give it a subscript of over here, ice water. So go to the alphabet part again. Ice water. Long name, but then you'll know exactly what it is. Okay, and that's equal. So now that's defined. So then I can just take the 540, which is a nice round value, and then just divide by that variable I defined. So Q, that's in superscript value. Let's undo that. Turn off Capitalize. There we go. And then write that whole thing out again. Now I'm wishing I had a shorter name, right? Ice water. On a computer, it's easy enough to copy it, but hard to do on the tablet. Our ratio is 1.7. No units because it's a ratio, right? Each of these would have units of calories that cancel out. As you can see, everything cancels. It's just 1.7. In other words, it takes 1.7 as much times energy. So like it's 170%, right? Because that's what this means, 1.7. It takes 170% more energy to just do that last step of boiling than everything that came before from way back at absolute zero. Right? Which I know I said before, but this is the actual numerical value, 1.7. All right. Well, I hope this homework help video has been helpful. Thank you so much for watching.